Thank you. Thank you for staying here, being here. I hope this is really what you want to listen to now. This is gonna be a talk where code is shown. Okay, that's fine with you. No coding is necessary by you. Okay, so lean back and enjoy. But some code will be shown. Fine, great. Thank you. Yes, so this might sound a little bit cryptic. And that's what Germans probably are well known for, cryptic language, like Heidegger, philosopher from the 20th century, very cryptic. I didn't understand him. Husserl, phenomenology, I didn't understand him ever. Okay, so I'm going to get in line with them and tell you some cryptic stuff about software development. But before that, I mean, you came here, you don't know nothing about me, right? I'm not Scott Ambler. I'm not one of the signatories of the Agile Manifesto. You don't know anything about me. So let me break the ice a little bit by telling you 5 facts about me. One is I was the editor-in-chief of the largest German Visual Basic magazine back in 2000. Wow, it's probably 15,000 subscribers. Yes. Okay, but back then that was a thing. I did that for 3 years. So I was writing already, and then I wrote some more. I wrote a couple of books, and I wrote hundreds of articles online and in magazines. So I'm pretty much a writer and a programmer. So that brought me also on stage. So in 2001, I made Bill Gates sweat on stage. Yes. Okay, maybe because I put on him this orange vest and took off his Armani suit. But maybe it was my questions. I don't know yet. Then later on, or even before that, I was a speaker at national and international conferences and from Las Vegas to Munich and Copenhagen and whatnot. And now I'm in India, like the culmination point of my career. It's gonna be probably over now. Thank you for inviting me. Then finally, well, this is where I've ended up. It's a small country here. It's 6 million inhabitants. Bulgaria and the Balkans and Europe, 6 million. That's like half of the people living in Bengaluru alone. So it's nothing. The Bulgarians are very welcoming too. We're living in a mountain town in our house. This is our view. So it's right the opposite of Bengaluru with its traffic all the time. Right, and the most important point why I tried to get here already in 2020 was this. I once had a crush on an Indian girl, but it was never meant to be. Okay, so but here I am, telling you something about, well, object orientation. And I hope at least the ones who stayed here, who came here, you are kind of familiar with this paradigm, right? Object orientation, great, yes. And I have to tell you, I'm going to differentiate between mainstream object orientation. I'm very sure you're an adherent of that, and some other form of object orientation, which I'm going to present to you, as a solution to a problem. And this problem, I'm going to tell you about after this roadmap through my presentation. We're going to start with some motivational slides, so you get really into the mood. Yeah, I want to learn about this. Then I'm going to tell you about an invention this obscure guy here made in 1967. Yes, back then. I'm going to unpack his vision. Some concepts get presented. And then from that, I derive what to do with those concepts in your daily coding practice. And then, if we still have time, I don't know, sometimes I'm talking faster and then slower. If we still have time, I'm going to show you how to apply all this to a code base. How that code base will look differently than, well, your code bases probably are looking today, okay? So let's start at the beginning. Let's start with this. This is a LinkedIn post from, well, a couple of weeks ago, and this sounds really bad, really. You are software developers, and he says, the Anthropic CEO, you know Anthropic, Claude AI, this guy said, well, in 12 months, AI is gonna write all the code. Fuck. What are you gonna do? Like lying in the sun, getting a tan, or just playing with your kids. What does this say about you, us, software developers? That's his prediction in 12 months. We are out of a job almost, except maybe for 10% high achievers. And he's even calling this an extinction event. Like first there was the dinosaurs and then it's software developers. Doesn't sound so good, right? I had a different image of AI and software developers. I had this image in mind. A beautiful marriage, right? What a tool AI is. Finally, we are getting like our trainee, our spouse we are supposed to live happily ever after with. Isn't that what we are, what AI is supposed to be for us, right? Okay, so for the other sex. So it's both ways around. Take your pick. Yes. And I could end my presentation here, but unfortunately, there are some problems. And the honeymoon phase is over, like the first couple of days with ChatGPT back in 2023, were so exciting, right? And then you tried it out and it was kind of disappointing maybe and didn't know why. And so it's not all roses. An extinction level event sounds pretty far away and then it's pretty severe. So what are we gonna do with this AI stuff? Is it good or bad? And are we gonna have a job? Okay, so let me unpack this. So I have a view here. What is the problem with AI? And there are some problems with AI. We can't deny that, right? So one problem with AI, and I think you all have experienced all of them once or twice or several times. Well, the notorious hallucinations. You prompt it for something, comes up with a great answer. You want to believe it, like the X-Files, right? I want to believe, but then it turns out to be not all correct. Damn it. And this is true for like facts you're asking for or for code. Sometimes it's hallucinated. Or it misunderstands you. Damn it, you were so clear, at least you try to be, but still some misunderstanding. Damn it, okay, have to reprompt it and prompt another and once more and so on. Or it made assumptions. You're getting a result, you say, what? This is not what I asked for. Why do you do it like this? I mean, with images, this is very, very clear, very fast. You say like woman on a sofa, comes up a picture of a woman on a sofa and you'd say, why is the sofa green and the woman has red hair? What? I didn't ask for that. So that's an assumption. And that's maybe even worse than the hallucinations because here you see right away, it's my fault. Right? You can't even point to the AI. It's my fault. I left holes in my specification. Then there's errors. Well, the AI is not flawless. Not flawless. Absolutely not. Like you and me, we are not flawless in our programming efforts. And finally, even though you might prompt it in a great way, there's no hallucinations, and you just say, well, write me the next Stephen King-like novel, which is going to become a bestseller, and it outputs 3 pages and that's it. What? It's not 800 pages like Stephen King usually writes, it's just 3 pages or 10 or 15, but not as much as you expected. There is limited output context, windows still, even though there might be million token contexts, the output is still limited. And that's not great if you want to have a Twitter clone built from one prompt. So there's problems with AI, yeah, but there's also, we shouldn't better trust it, and there's also problems with human code. I guess at least you can agree regarding the code of your colleagues. Your code probably is flawless, but the code of your colleagues is not flawless, and it's challenging to modify, right? You touch it, you change something, and you hope for the best. And you don't really know where to change it in the first place. It's hard to test. You don't want to hope for the best. So you want to set up a test, but it's hard to set up the test to check what you just changed. Is everything else still okay? No regressions, stability, retained. And what about the new code? Is that okay? Who knows? Can you test that really? And the code, before you're going to change it, it's probably hard to understand, very difficult to understand for different reasons, right? So that's the code of your fellow humans, not even AI code, human code. Okay? And then, where it's always so messy, and there's a problem with human coders. It's not the results of your colleagues, it's, well, your colleagues. You tell them something, you're a product owner, you're the customer, you're just a fellow, and you realize they are error prone, their code is not correct in the first place. They tend to misunderstand you for whatever reasons, maybe too little caffeine, and they are making assumptions, like AI is making assumptions, plus a very bad problem, and has been called the problem of premature optimizations as maybe the hardest problem in software development at all. We tend to take shortcuts and look into the future and already know what we're going to need in the future and optimize for that today. And it's not going to cut it. It is bad. We don't need it, costs time and money. So premature optimizations, really bad, happens with human coders because they're trying to predict the future, which is often failing. Well, don't trust them either. Don't trust AI, okay, don't trust the human coders, and, well, the code is too messy. This is really not a great pair, right? The two AI and human coders. What can we do with this? This probably is a more realistic picture of the marriage or the partnership between the two. I don't think it's much of a marriage. Either way, right? So it's not just the husband's fault or the wife's fault. So something is wrong with the two. What can we do about this? That's the question. What can be done? How can AI help us in a reasonable way to get not extinct? I personally don't believe in this extinction event. It's not that easy. But, well, there's some truth to it. So let's come back to the problems I saw. And here, let's start with how to deal with the AI. We had the limited context window. How do you cope with that? I mean, real in a practical way. How do you cope with the limited context window? It's very simple. You just prompt for a small scope of requirements. I mean, you don't ask for the whole Twitter clone, an SAP clone. No, you prompt for something much, much smaller. Okay. So what about the misunderstandings, the assumptions, and the hallucinations of AI? Well, we can counter that by being more clear, more specific, and more comprehensive. So it's on our side as humans to think much better, in a much better way, about requirements. Okay? What to do about the errors the AI inevitably is going to produce? Well, set up automatic tests, right? We know that already. We're going to do the same with human code. So be super specific as to be able to set up automatic tests. Automatic tests are requirements of a different kind. Okay? So there are ways to deal with the AI code results. And let me further make that specific. I would say a small scope is immediately a countermeasure for a small output window, but it's also a small scope which helps us to become clear, comprehensive, and specific, breaking it down. And it's a small scope we can really set up specific tests. So become small, small, small in your requirements. Okay? What about the human coders? They are suffering from misunderstandings and assumptions too. Well, we have heard about this. Become clear, comprehensive, and specific, right? It's the same. Has always been the same. What about the errors? Well, for 25 years, we have been advocating automated testing, yes. First starting with the Java frameworks like JUnit, automatic tests become super specific for those automatic tests, and then premature optimizations. Well, how can we counter that? It's so deeply rooted in human nature. I would say you can counter that with clean code principles and reviews. Sit together with your colleagues and review the code to try to spot the premature optimizations. And maybe design, so think about your coding beforehand. And what does that boil down to? Again, it's small scopes. You can be clear, comprehensive, and specific. Small scope, so you can set up automated tests. Okay? So there are ways to deal with the shortcomings of humans. What about the human code? Challenging to modify, yes. Difficult to understand, hard to test. What can we do about that? Ha! Damn it! It's small scope again. So small scope makes it possible that we can really get a grip on our dependencies within the code, right? There's so many different kinds of dependencies, runtime dependencies, design time dependencies, logical dependencies, all sorts of dependencies. So as to be able to really have them all in our view, the scope has to be small. What about difficulty to understand small scope? So for a small scope, you can come up with good abstractions. Good abstractions like where one word tells you the whole story and you understand what's going on. And hard to test, well, small scope, right? In a small scope, whatever is in that scope, you can test more easily if that's small, and you can set up comprehensive tests with good coverage. Okay? And, well, find good interfaces for the small scope. What's the interface for a whole program like SAP? I don't know. But for a repository in there or some domain logic in there, yeah, I know what interface to define for that. Okay. So there are countermeasures to those shortcomings of human coders and AI coding. Great. Okay. So it is possible, I guess. And let's focus on what's needed for that. I think it's small scope, really boiling down requirements to the essential again and again and again. And that's a matter for developers, and that's a matter for product owners, and it's really a discipline. Plus, okay, what do we do then? Well, coming from there, we check that we don't get overboard with our dependencies, and that's a very important topic further down in this talk. Great abstraction, easy to understand, distinct interfaces, easy to test, plus, well, yes, testability is where it all starts. So if you wanna label clean code development, which came up sometime around 2006, 7, 8, with Robert C. Martin's book, Clean Code. If you want to break it down to one label, it is testability. And testability, it all starts from there. Because you want to get to testable code, you will need to think about simple dependencies, modularity, which is about distinct interfaces and great abstractions. This all makes clean code. And this is so much easier if you're just focused on small scopes, okay? So this is like setting up the stage. This is the whole motivational part. I want to focus on this part up there, testability, and this coding stuff, modularity, simple dependencies. Because I think billion-dollar mistakes have been made by through mainstream object orientations in that area. That's why we are suffering so much. Something has gone on and has gone in the wrong direction. Okay, let's do a little journey back in time. Who was born in 67 already? Okay, one, two, okay, me, as you will see in a minute. So this is stuff that happened in 67, plus me chilling on our terrace. I wasn't yet into programming, just getting together my energy for that. But in 67, not only the Beatles were a great band. Dustin Hoffman started his career. No, also there was this guy. Who knows this guy? Who knows Alan Kay? You know Alan Kay? Yes, you get a prize. You're the only one? Okay. Alan Kay. Alan Kay is the father of object orientation. At age, I don't know, 26, around that, he came up with this term, object orientation. It's all his fault, we could say. It's all his fault. So this guy, he was like a multi-talent. He said this. And who would have thought, right? Let's look at it very closely. I thought of objects. Yeah, we know what objects are, right? So being like biological cells. What? Objects being like biological cells. That was his idea? Come on. And or individual computers on a network only able to communicate with messages. So messaging came at the very beginning. Who thought about object orientation in terms of messaging? Okay, not so many hands raised. How come? It was the core idea. This guy had a bachelor in molecular biology, so he knew what he was talking about. Before he got a master's in a doctor, even a doctor in philosophy in computer science. So this was his idea. And from that came Smalltalk, and from that came C++. And he explicitly said later on, C++ is not what I had in mind. Okay, sorry, Björn. So Alan Kay said this. I thought of objects being like biological cells. And we have now Java. Huh? How does that match? Or C#, or TypeScript, Python. Is that like, do you see biological cells in there anywhere? No. Okay, so that's why I'm here. This is the revolution I want to bring to India. The revolution. That's my daughter. She's so ashamed by me now. The revolution of radical object orientation. Radical because it's going back to the roots, radix, Latin. Back to the roots. And for that, I want to conjure up the image he had in mind, right? Objects being like biological cells. So here are biological cells. That's the so-called neuromuscular junction. There's a nerve cell and there's a muscle cell, right? So you all have that in your body right now. Your heart is pumping, your arms are waving, whatever. So it's all working great. That's what he had in mind. One cell and the other cell communicating, well, cells are communicating through, for example, neurotransmitters. One is acetylcholine here in this example. That's what he had in mind. What? Does that resemble in any way your code? No, right? No. Can it possibly? Well, we have to see. But one day, like 2012, I woke up and thought, this was a great idea, but I don't know why. I just had this feeling, this must have been a great idea. So I tried to deconstruct it. What did he really mean? And so I first mapped it onto not boxes and lines, but ellipses and lines, or circles and lines, right? So here is a schematic view of a nerve cell, and here is a schematic view of a muscle cell, right? And now for the important part, a schematic view of this, where there's biological cells communicating using messages, and that's this here, right? So this line here is the communication line. And there's, from this nerve cell, acetylcholine flowing to the muscle cell, innervating it so it contracts or whatever it does. Okay? So this is happening billions of times, all the time, in our body. That's what he had in mind. So what do we have? We have an object here, nerve cell, an object here, and a message there. That's what he had in mind. what does it mean? Can we map that to software development? It seems impossible. Smalltalk didn't look like that, in my view. C++ doesn't look like that. Java doesn't look like that. It seems impossible, but it is, in fact, very easy and transformative. Okay? So, buckle up. We first have to consider, so something is happening inside here. So these cells here, these objects are the workhorses, pulling forward the software. They are creating the behavior or parts of the behavior of software. Right? What's the behavior of software? I'm going to show you. I'm poking into his eye, and he's going to smack me. That's behavior. So I'm triggering him, and he's smacking. I'm giving him an input, and he is giving me an output. That's behavior, right? So all those cells are part of a reaction chain. Something is triggering software from the outside, and somehow software reacts by outputting, well, something, data, probably, somewhere, right? On your screen, maybe. So this is part of the overall behavior. This is part. Something is happening in here. We're going to look at it, what that is in a minute. But, well, yes. So this is active. This is active. In the body even, it's active independently, all autonomously. Each cell is like a processor, a computer in a network, working all by itself. Right? That's what he had in mind too. And then, well, it outputs a message, and the message is received by another cell. Here comes the first principle we have to focus on. Let's go back to Alan Kay. Don't take my word for it. Take his word for the truth. It's only able to communicate with messages, and messages came at the very beginning. Look up object orientation on Wikipedia. You find the term message in there, but it's like, okay, messages are methods. That's it. That's not enough. Not by far, not enough. And the big idea is messaging. So what the hell is messaging in the first place? We really have to come to terms with that. And now I'm going to show you what messaging is not. And this here, this is what you are doing all day long in your object-oriented code. It's you have one of your mainstream objects which is sending a request to another mainstream object and then getting a response so it can... Thank you. See, I couldn't continue my presentation without the service of my lovely daughter. So I send an implicit request to her to support me with something, in this case, water. So now I can continue my presentation, right? So we had a functional dependency. I had a task to fulfill. I couldn't do it, couldn't continue, had to rely on her service. Now she delivered, and I can continue my service. So that is functional dependency. We have that all the time, and this is not, repeat, not, emphasize, not messaging. This is the messaging he had in mind. Radical object, whatever that means, is sending a message somewhere, and another radical object receives it, and that's it. No return, no acknowledgement, nothing. Just one way, unidirectional. Messaging is unidirectional sending of data, not bidirectional, unidirectional. And that is missing from all your code bases. And that is, unfortunately, the problem. We are not modeling, like Naresh alluded to, not modeling software in the image of machines. We are not. We are modeling software in the image of organizations. You know how an organization works. It's management, and management tells you what to do, then takes your result, does something with this, gives it to you, tells you what to do, you come back with something, management does something with the result, gives this to him. So management is micromanaging much of the time. This is happening all the time. This is how our organizations work. Management is not putting you and you and you together in a great process and leaning back and letting it all happen. This is not how management is working. It's not how organizations are working, especially not in the office. So this is how we model software according to our organizations, not according to how machines or organisms are built. But that's what he had in mind. He had in mind this. Okay, that's the future. Okay, here's a first image of code, sorry. What is this code in general? It's not all of the code, but in general what it's doing is it's taking a list of cycle times, like how long it took to implement an issue in your software development. So there's a long list. This issue took 3 days and 5 days and 3 days and 1 day and 6 days and whatnot. So it takes this long list of issue cycle times and shows a histogram of that. That's all it's doing. Very, very simple use case, right? So and this is the code or part of the code, and there it says calculate distribution or histogram. So it calculates this over there, at least the numbers for that, doesn't do the displaying part. And here's the logic, right? So you would recognize this as logic. This is the code which actually does something. It manipulates data, right? So this is data processing. And then here, there's something else is happening, something else down here. There's a call, right? There's a call. There's this logic here in that function. Then there's a call to that logic to a service, like I called up my daughter. And this is doing something. And then this method continues, does something more, and returns some result. That is what I call functional dependency, because a workhorse part depends on another workhorse part. And my question to you is now, how do you test this workhorse part? Only this. How do you test that? Only that. Is that possible? How is that possible? You tell me. Dependency injection, right. Dependency inversion, something needs to be injected, abstraction, yeah. Okay, I know, yeah, right. You have to do that. You cannot otherwise just focus your test on this. Tomorrow is the talk about software architecture, where I'm going to argue that dependency injection is so 2000, we're not going to do that anymore. Great. So you need to replace this with a surrogate, you call it whatever you like. So it's not the real thing, then you can focus on this. So that's adding complexity. Not good, not good. Okay. So that's what I call functional dependency. Okay. This abounds in code, in your code. Makes it hard to understand, difficult to test, not good, not fun, not at all. Okay. And this is absent by definition, based on principle, from radically object-oriented code. Because radically object-oriented code has just this flow. Something happening here, no dependency on anything, then something happening here, no dependency on anything, then something happening here, there's data flowing out, then something happening here, and there's no dependencies at all. Nothing. Just data flowing forward, unidirectionally, that's it. No dependency. That is what object orientation means. Who would have thought, right? Alan Kay promoted data flows, laying out functionality horizontally, whereas back in the 60s and in the 2000s, your code, there's functionality laid out vertically from a top function to a bottom function, deep down there, hundreds of levels deep. And that's why debuggers are such great tools, because you can stepwise go down those function call hierarchies at runtime or test time and so on. You need to do that to understand the control flow. But control flow is so 2000, we want to have data flow, okay? And sorry, I didn't point it out. This principle here, or this layout, where messages are flowing just unidirectionally forward, downstream, where this cell here, or object, does not know anything about that cell. No nerve cell knows which other cell is going to consume its acetylcholine neurotransmitter, and no consuming muscle cell knows where the acetylcholine it's receiving is coming from. They are mutually oblivious to each other. And this is not the case with your objects in your code, not at all. So this is the first principle I derived from Alan Kay's vision. Sorry. And now on to the second principle. Because the question here is, there's one question. And that's the second principle. I pondered this image so long and asked myself, what's missing? Something is missing. There needs to be more in this. Something is missing. What is it? And it is the obvious. Well, no, not so. It's hiding in plain sight. The question is, who's putting this together? What? Who's putting together the network, this data flow? Who's setting up a connection from here to there? Who is that? Who's that in your body? What's doing that so you're not just a puddle of fluid on the floor, but an actual form? No, it's not your skeleton. It's connective tissue. There is a special type of cell and molecules in your body which sole purpose is to keep things in line together so they are functional. And that was missing in his image. He never talked about it. He never explained what this messaging meant, so I had to deconstruct his message. And he never talked about this, the necessary ingredient that whatever the objects, like however the objects are connected, that is a responsibility in itself. And that is integration. So this being connected to that is a separate responsibility. This has the responsibility of doing something. This has a responsibility of doing something else. And then there's a third responsibility, namely integrating, composing from those parts a larger whole. That is a separate responsibility. And it's a very important responsibility. There are operators in functional programming languages like F#. There's an operator for that, the composition operator. But it's not so very popular. Composition is, I would say, even though there is this operator, not so much talked about. But here it's very clear we need a separate compositional responsibility to build up our, well, radically object-oriented networks, data flows. You heard about the single responsibility principle ever? Yes? Yeah, solid principles. Yeah, right. The S, the first one. And then is what? OCP, Liskov, right? Dependency inversion principle, interface. Okay, S. Single responsibility principle. It's so important. It is really important. But who can tell me what a responsibility is? What's a responsibility? If it's a single responsibility, you sure can tell me what it means to have a responsibility. What? Take ownership, yes. Of what? Of task, yes. But what's the task? Robert C. Martin, I don't blame you. Hardly anybody knows. Robert C. Martin didn't even explain it. He had like 3 different definitions of the single responsibility principle, and none of it made it really clear. None of it, I would even say, made really sense. But it's a really important principle, and the decisive word here, which never is mentioned, is decision. Responsibility means being responsible for implementing a decision that the customer made. I'm deciding this should be displayed as a bar chart. Okay, so that's a decision because it could be different. It could be a pie chart or no chart at all, whatever. So it's a decision, show me a bar chart. And then I can ask, so where's the code unit responsible for implementing that decision? And well, there's maybe some class or whatever. And we can break that down, and there's lots of responsibilities in software, yes, very great. And there's one more responsibility, and it's implicit so far, and that is the responsibility of how to put together different parts, different building blocks in a software to create a larger behavior. And that responsibility I call integration. And there's integration is one aspect of a more general term, which is composition. And we have, in this image here, there's 2 compositions. This one is composing logic. Let me go back here. This is logic composed by this function. And let me go forward. And this is other functions composed to another level of functionality and behavior. So, okay, this is the schematic view. And your question is, what is this? I mean, this circle, this ellipsis, how do I implement this? What is this and what is that? How do I implement that? And the mapping is very straightforward, very. Both are functions. And one function here, the inner circle, is a function composing logic into whatever the function says is supposed to happen. And the other function is composing logic into whatever they're supposed to happen, here, right here. And then there is a third function. The third function's sole purpose is to put both other functions together. That's all. And that's really enough. That's the integrational responsibility. Question? Indeed, request response is happening. Like this is calling the function request, is returning, responding with this, and that's putting the data in here. So technically you're right. There is a request response happening. Damn it. So why am I not calling it like that? Because there is no logic working with this response. That's why I'm not calling it a request. I could put this call right here. So I don't even create a response data structure or a response variable. Pardon?
That's the reason you have mentioned that as data flow.
Yes, yes. That's why I'm calling this a data flow and not request response. This is our meager way of implementing it using a 3GL, unfortunately. So I'm trying to keep what you have at your hands, a 3GL, C#, TypeScript, whatever. But you see this form here, 2 function calls right after another. It's looking very different. It's very easy to understand. You read this flow from top to bottom. And that for me is quite important. Read from top to bottom, like a book, from top to bottom. Even in Chinese, from top to bottom. And don't try to be smart and optimize away this here by putting it in here, because then you destroy your natural flow of reading. You have to switch between top to bottom, right to left. Not good. So stick to top to bottom. And I'm telling you one thing, these kind of functions will never grow beyond 10 lines. Okay, 11. Never. Because after 10 lines of calling other functions, you get bored. No, you lose track. You say, what? I don't really get it. What's happening here? First 3 lines, second 3, what? So you will refactor it. We see an example later on. You will refactor it, and it's very easy to refactor. And I'm telling you, these here, they are called integrations, and they are called operations. These functions here will never grow beyond, let's say, 30, 50 lines. Because then you'll feel, I don't get it anymore. What's going on here? So you want to refactor it, which is great. Pull out, extract the function, great. But then, according to that principle, you have to turn it around and make this an integration itself. You can't have it both. You can't have, like up here, have logic plus a function call. Nope. That is functional dependency. Nope. Not gonna be there anymore. With the integration operation segregation principle, you either have function calls or you have this kind of logic. That's it. So if you have an operation and extract one function for 10 lines at the beginning and want to keep 20 lines at the end, logic, nope. You have to extract them too, and here you go. It's a clean integration. Question? The segregation means you either have integration or you have operations. It's not a mixture. You don't mix integration, calling another function, with logic. No, segregation. Sometimes segregation is good. Not on bus, but here. Segregation is great. Okay? No functional dependencies. Workhorse, logic, no workhorse, just data flow. Using a 3GL. Okay. So here you see it. This larger ellipsis here, or this shape, is dot up here. Those smaller inscribed shapes are the function calls, and data is flowing, parameter in, return value out, return value, some parameter goes in here, return value flows out. That's the natural translation. Right from Alan Kay's definition of object orientation back in 1967. Who would have thought? Unfortunately, this got buried or never understood, never implemented. People don't program like that. Unfortunately, because this makes for great understandability. I find that very easy to understand. It leads to small function. I find functions containing just logic, which are just 50 lines max, very easy to understand compared to the functions you have, which are 500 lines or 1,000 lines or 5,000 lines. Who has seen 5,000 lines long functions? Anybody? No? You never? Okay, I've seen them. Yes, they're out there. So even 500 lines, it's very, 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 very hard to understand and test. Parts of it, how to test them. You can't do that. So this is easy to understand. This is easy to refactor. And to keep some logic inside a bubble like that, it's very easy. Okay? So this is the result. Objects are forming hierarchical data flows. That was his vision. You see here, there's logic, workhorses, and then there's those integrations, the compositions, putting together 2 workhorses, another 2 workhorses, and then, well, the integrations themselves are put together with another workhorse over here, so it's bubbles all the way up or bubbles all the way down. And the implementation is functions all the way down. It's functions all the way down. I could even say, well, radical object orientation means functions first. Not objects, functions first, because functions are the way to implement those objects. And this is very natural and mirrors what's happening in a body, in an organism, how that is built, and it's even matching how a car is built from small parts which get integrated, composed into larger parts, which get integrated, composed into yet larger parts, and so on, until you have a whole car. And depending on your context, you're talking about a whole car, or you're talking just about a motor, or just about a spark plug. This is kind of hard to draw using a whiteboard program. So I like to draw it like this. Here you see the hierarchy. You're used to that kind of image. And now we have to differentiate two types of relationship. Relationship number one, we have seen that all along. That's this here, right? The arrows connecting objects, the radical objects of L and K, objects together into a data flow. That's the arrows here, horizontally. And then there's vertically, as you can see, not arrows, but those lines with a dot at the end. And that is, well, that's a usage relationship. Up here, this one, well, needs to use this one because it connects it to that one, because it connects this to that one. So the usage is only, or the knowledge relationship is only there because integration needs to happen. I can only integrate you three into a workflow if I know you, if I can advise you. Okay, please do this, and you that, and you that, and you three work together. Let me go on vacation while you're working. Okay, so that's one kind of relationship, knowledge relationship, usage relationship, but usage only means here in this regard using for integrational purposes. So this is doing the same with those two units here, and this are objects, and that's doing the same down here. Non-functional dependencies, because if you implement this, there's no logic in that. Logic represented by the workhorse is only down there. Let me make this very obvious. Green means good and easy, and red means danger, risk. Down here, it's risky because down there is logic, and logic is hard to understand. You have to simulate it in your head. You have to put tests to it. Danger. And up here, integration is easy. You can read 3 lines. Do A, do B, do C. Is that right? Yes, okay. So how difficult can it be? Do you need to test that? No, you don't need to test that. In most cases. You can set up a test up here. It's an integration test, yes. But you don't need to set up an integration test here and there and everywhere. Don't need to do that. Most importantly, you set up tests down here. So integrations, green, great, good. Operations down there, red, risk. Okay. And now back to code. Oh. See, there's 3 lines here. Okay, run. 3 methods or functions get called. And see what I did? Create buckets, right? Distribute to buckets, visualize distribution. I extracted those 2 calls here to a new function. No, the other way around. I extracted those 2 calls here to a new function and call it up there. So refactoring is very easy with integration. You just pull out 2, 3, 4, whatever consecutive function calls, and that's it. Very easy to refactor. Down here, the operations, integration, just function calls, operations contain logic. Well, they are all small. That's easy to test. Very, very focused functions. And do you remember now, right from the beginning, what was the problem with AI and humans? Too big scope. And now we are down to very small scope. Because there can't be big scope anymore with logic, because logic is confined to the bottom, to the leaves of this integrational compositional tree. It can't be like an intermediary functions. No, it's not possible anymore. And so the logic is right there only at the bottom and can be tested easily. Oh, here, oh, now come on. Here, I set up tests for this function, I set up a test for that function, very easy, and no surrogates needed. There is no dependency anymore. I'm testing the function, the logic inside the function, and that's it. No dependency injection, nothing. Okay. Now what you're, okay?
Develop the code this way, you don't need to do that much integration testing type.
I don't need what?
You don't need to do that much integration.
No. I don't need to do that much injection. That's what you mean, probably.
I meant integration with that.
I need to do integration here. That's integration, that's integration, that's integration. But I don't need to do all the integration tests. No. No. You will see, in practice, this is kind of theoretical. I'm talking to you about this. This is the first time you see this. I've done that for the past 13, 15 years. In my practice, I don't need to set up tests here and here and here. No. I'm testing down here, and I'm testing maybe up here. But this can be many more layers. And when I'm testing up here, you could say, oh, Ralf, hey, up there, this is all dependent on all the logic down here. How are you going to test it? You need to replace something. You need to introduce surrogates, mocks, stubs, whatever, fakes. And I'm telling you, no, I'm not doing that. Because the point is not to test this comprehensively. This is not about coverage. It is about, well, only integration, which means, does this work together in principle? As long as I can see that, it's all just fine. And that I can see with an integration test, which actually even accesses resources. So I'm rarely, maybe I'm exaggerating a little bit, I'm rarely replacing even resources in integration tests. I let it run through, I see, okay, the resource gets called, right, great. I don't need to cover the resource with tests. That I do with operation tests, which are then not dependent on anything anymore. Okay, one thing you have been missing so far, and you haven't rebelled, you didn't spring up and say, oh, there's something, where's classes? Where are the classes? Isn't object-oriented programming supposed to be about classes? Unfortunately, Alan Kay said explicitly, I'm sorry that I brought classes up in the first place, and objects. It's not what this is all about. It's about messaging. And he didn't even invent classes. It was somebody else. And it wasn't in his first definition. He was talking only about objects. So what are the classes about? There's one thing missing I have glossed over so far. You see that in some early images here, for example. See, I put in state, right? Okay, there might be state. Objects, nerve cells, muscle cells have state. But how can a function have state? I'm focusing so much on functions. How can they have state? Well, there are means to give them state, but you don't want to use that much. So yes, we have to talk about nouns. We have to talk about a container for functions. That's where nouns come in, that's where classes come in. Yes, so nouns, suddenly we are not talking about a verb anymore, we are talking about a noun, and you see what happens now Whereas in the data flow with verbs, it flows forward, only forward, one direction, unidirectionally. You can see there's a loop. That's happening when nouns come into play. Unfortunately, it can happen. It doesn't need to happen, but it can happen. But that's okay. On that level, we don't really need to know. This is not showing how behavior is created specifically, but in general. You see the UI is somehow connected to the calculator, and that's somehow connected to the storage here, and maybe over there, I don't know. This is just part of a larger picture. Okay, great. So we have nouns here. Between the nouns, messages are flowing. See, I prefixed it even with like a functionality. Okay, you need to sum something. You need to average something. You need to load something. Okay? That's more like messages as we used to think about them, right? So there's semantics connected to them. Okay, but let's break that up, or let's break it down, zoom in. So there's one of these objects here, the noun object, and it has receptacles, it has connection points. There is a sum connection point, there's a message coming in, and it has an average connection point, some data flowing in, and it has output points, well, I don't know, secretion points, where data is flowing out. And that's messages. Next step, we're going to internalize this, and now you see, okay, now I know this is a proper object. This is a proper class. There's the class calculator, and the class calculator has a sum function, and the class calculator has an average function, of course, and there's data coming in here to the sum function, and data flowing to the average function that's producing some results. Okay, so there's the explanation why we have a noun as a container for this here, which is actually doing the work. And this container can, of course, keep state. That's what an object is doing. This is also what a static class is doing. So even the objects, the classes you instantiate in a mainstream object-oriented program are not necessary just to associate state with a function. It's nice, it's good for testing, but it's not really necessary. The idea of radical object orientation even works with static classes or modules because it's about the flow of data. Okay, so this is messages become functions, right? So published, there's this sum function published to the outside on the surface of this calculator object, you could say, and there's stuff flowing out, some results flowing out. Now check how this can be implemented. And here we have a very, very generalized, I have to emphasize that, a generalized version of a calculator noun. And this calculator noun understands the average message, here, average, and the average message receives some data, a list of numbers, and outputs a list of a number, okay, but it also, here, this calculator noun also has an output where this is here a continuation function, a function that gets called, you could say an event handler or a callback that gets registered here, event listeners, and gets called with results. That's a very general implementation of outputting data from an object. Call another function. But you don't know what that function is doing. You don't have a clue. You just say, call this continuation, call this event handler here. That's a very, very general implementation because, well, a usual implementation just set up a method which takes some parameters and returns a result. just do it, it's so easy, that's great. But it does not allow for alternative results and not for multiple results. But that's essential to the idea of Alan Kay, because he says, well, it's like objects are like biological cells which can fire or release neurotransmitters in any number in reaction to a certain trigger, and they are working autonomously, once triggered, autonomously. And that's like a computer. You trigger a computer, it can produce any number of results. So why not a simple function? And that only works if I kick off the function, it starts to run, logic is working, and it's calling an event handler, a callback, to push out results whenever a result gets produced. Can you imagine? This is like an actor. Have you heard about actors? Actor frameworks? Okay. So actually Alan Kay said that later on. He said, yeah, maybe actors is more what I had in mind when I coined this term in the 60s. But we don't always need asynchronous computing, so we live with synchronicity, that's great. And the most simple translation for the radical object is a function with the parameters coming in for the message it receives and a result flowing out. And since those functions work together using unidirectional data flow, there's no request response. They are easy to test, and they get composed into higher levels of behavior using integrations. So that's the sum of it. It's about functions first. Functions connected in data flows, that's called composition. Plus functions grouped in classes, yes. They are the classes, finally, thank God, which is an aggregation. Both is abstraction. Composition is one form of abstraction. It's behavioral abstraction. It is for your convenience. A car, the car you step into today, and you just press a button and it goes off, that's a so high abstraction compared to what you had in the 19th century. And it's all, well, invisible to you. All those layers invisible. That is what composition is about. And aggregation, so this is composing complementary parts. Parts which are different and are put together to form a new whole. And this here, aggregation, is a different kind of abstraction. Aggregation puts together similar parts, similar in some regard, to form abstractions. And similarity can be, well, we both share state. We both share resource access. We both share a file access, state. We both share a common theme. We both share the responsibility to implement a certain decision, like displaying a graph. And different functions are needed for that, not just one function with all the logic in it. So that's a reason why there might be a class needed to aggregate all those functions into one. We have to keep in mind, right? There's this AI thing. How does it help with AI? And I submit to you that it helps because it makes it very clear how you should define small scopes. That was the start, okay? We need small scopes, and those small scopes need to be easily testable. So we have, well, this won't go away with AI-generated code. We have a hierarchy of functions. This is not all just one big function containing all the logic. AI will never generate that code. And in the foreseeable future, I don't see AI generating code which we don't care to look at. And as soon as you want to look at code, It can't be 5,000 lines. No way. And as long as you want to look at code, you want to be able to test that code. And it can't be 5,000 lines of code you want to. No, it needs to be fewer lines. And that's what's down here. Low abstraction classes, and I now mean the classes you know, with functions which are operations with regard to the integration operation segregation principle, which only contain logic. That's the purpose of those classes, to primarily contain functions which contain just logic and no functional dependencies, which can easily be tested without any dependencies, without any surrogates, mock stubs, whatever. And AI doesn't know that. And so you have to prompt it for that. Okay? Next level is somewhat higher level abstractions, which already integrate. They compose from the low level parts, but there's some operations in there, but mostly it's integrations, and yet higher level abstractions, which only integrate. So the boxes here stand for classes. Inside the boxes are functions. Inside the boxes are mostly functions which are red and operate, some red, some green, operations and integrations, and mostly or only green. That's what you want to see in your code. That's what you should prompt for explicitly. So you have to, well, in conjunction, in a dialogue with AI, you have to go through the design process still yourself. Think about the small output context window. You can't get a whole application produced in one go, no. So you have to think about the parts you want to get produced. First this part and that part and that part, and then telling you which kind of parts you want to look for, and it's such kind of parts. I'm telling you something about the form of those parts. And that form is, well, suggested by radical object orientation, by what Alan Kay in the 1960s had in mind. Okay, we have another 50 minutes, right? Yeah, okay. So 50 minutes. We'll see. This is now the dirty part with some code. Let's see how far we can get. This is some requirements, okay? Let's have a quick look. It's flow time forecasting. How do you do estimations nowadays? How long it's gonna take to implement those 5 issues? You do that today? Estimations, what do you do? Story point estimations? Be brave, say yes. Okay, we're doing that? Yes, okay, I'm so sorry. Yes, yeah, okay. You get a big hug from me. I'm sorry. So I'm suggesting with this small example here, some kind of different form of estimation. No, actually it's no estimation, but it's trying to predict the future. So it's a different kind of prediction, which is the category word for estimation and forecasting. And forecasting is like weather forecasting. How does weather forecasting work? There's a model, right? It's not some who gets asked every night, what's the weather gonna be tomorrow? No, there's mathematical models working with data. Okay, and those models forecast with certain probabilities how the weather is gonna be tomorrow. Maybe 80% rain, but 20% sunshine, who knows? And that's what's behind those requirements, a forecasting model for how long it's gonna take to implement 5 features. Let's read, okay, this forecasting, this prediction type is based on historical data, so we input how long it took us in the past to implement features. Yesterday the feature was 2 days, before that it was 3 days, 5 days, 10 days, 1 day, 2 days, and so on, into infinity, whatever. Up from 25 such data points, it becomes kind of reasonable forecasts. So if you collect this data, we are starting that's what this is actually saying. We are starting a feature today or an issue today, and we are finishing it today. And today we're starting another one, and we're finishing it, well, some other day. If you just record this on, off, on, off, on, off, on, off, in an endless list, like events, it's the starting event and the finishing event. If you just record that, well, we can do the forecasting by calculating the cycle times, how long it took, and calculating a distribution. How often was it 2 days? How often was it 3 days? How often was it 5 days? Maybe never 1 day, but 10 times 3 days, and so on. We can calculate that as a distribution, no, to be more precise, as a histogram. And then from there on, we can ask, okay, let's not look at just one feature, look at 10 features. How long is it going to take to do 10 features with this kind of histogram? And then this forecasting comes up with an idea. And with a very differentiated idea, because it doesn't tell you it's going to take exactly 25 days, but it takes 25 days with a probability of 50% or less. And that's like throwing a coin, right? How much would you bet on heads? I wouldn't go for that game. So what is a game you would, well, bet something on, like $10, 100 rupees, or 1,000 rupees? How much would you bet on getting 6 when you roll a die? Would you do that? No. But if I tell you, you can double your investment, your bet, if I roll 1, 2, 3, 4, 5. Not if I roll a 6. Would you go for that? Well, it's 5 out of 6. That's a great game, right? That's a probability of 87%. So looking at a distribution of cycle times for 5 issues, where I can tell you it's going to take 30 days or less with an 87% probability, 0.87, I would go for that. That sounds reasonable. Can be 30 days or less, maybe 25, but 30 days, not at most, could be 50 days, but with a high probability. That's what this is all about, okay? So I'm telling it, well, this is the general idea, how the user wants to interact with the app, how the data is going to be stored in a certain event log here, some JSON data, and how the data is going to be visualized. See here, this is this distribution or the probability distribution or histogram, and so on. That's what I'm describing. That's the requirements, right? And now I did 2 experiments. 2 experiments, okay, each 5 minutes. Experiment number 1, a one-shot prompt. One big gun. And that's, well, my chat with the AI. And these 3 pages are exactly what you just saw. The requirements I printed in text. That's what I threw in and maybe said, okay, now generate some TypeScript program. That's it. But it were exactly it was that text, okay? And this is what the AI generated. This is all the code. Huh. It came up with a solution. The solution is even working. Oh, crazy, right? So maybe the Anthropic guy is right. All the code is going to be written by AI very soon. Let's prepare for some vacation days. This is how it's looking. I could show you that interactively. Interactively it takes longer, so take my word for it. This is how the code is running. So I started the program, and it's showing me some menu, and I choose a menu item. I enter a new feature when it's starting, and then I choose another menu item. Now I'm telling it when it's stopping, and here I want to see, okay, what's the histogram at this moment, and here what's your forecast. This is what's so interesting. What's the forecast for 4 issues? It did the job. I just told it the requirements. Wow. So what's my bloody problem with this? Well, it generated some code, it made assumptions galore, and I don't have a clue where things are located. So, okay, it generated three files, app, forecast, storage. Where did it get this idea from? Maybe it's not that bad. So there's a resource access here. This is kind of domain. And this is some form of composition. Oh, not that bad. Okay. And down there are some types. And oh, wait. What the red clouds here are showing, you know that by now, the red clouds are logic. There's logic in there. Okay. Zoom in. This is now the classes inside those files. So there's no class in here. There's one class in this file. There's in that file, the second file, there's two classes. Okay, what do they mean? What are they for? There's a dependency between those classes, and you see both red clouds. There's a functional dependency here, hard to test, not good. Some dependency down there to data types. And now it's functions, and I'm focusing on this multi-issue forecast, how long it's going to take for 4 issues to be implemented, to get them implemented. So which functions are getting called? It's the main function here. Oh, no, it's two use cases. One use case is starting an issue. That's calling the add event function here. So it is something in the user interface is calling something in the storage. This awfully sounds like the layered architecture. Is that good? Functional dependencies between user interface and storage? I don't know. So here, multi-issue forecast. This is user interface again with lots of logic in it, calling the domain logic, yes, okay, and also calling the storage logic with two classes, calculate flow times of issue tracker and then the event store. Lots of functional dependencies. It's working, great, but, well, seemingly, I don't know if it's really correct because there are no tests. It just happens, so it's kind of working, and I was very happy. Just one shot, great. But this is a tiny example, right? Tiny. I don't trust it, not really. So what to do? What's the alternative? Functional dependencies, this is hard to test. How should I test this? There's a function call here to the forecaster. This is domain logic. The domain logic, as we can see, oh no, it's not calling the storage. And there's more here. How can I test that? Possibly, it's impossible. Okay. So this is a better way, right? Death by 1,000 cuts. Not just one prompt, but well, this is the second approach. It's some more lines, right? Some more pages. It's 71 pages of prompting and responses. That's iterative development, right? And this is how we usually do it. It's nothing new. But now I'm doing this with AI as my partner. And now I have to have an idea how to prompt for small scopes so I can be specific and clear, and there's no assumptions springing up, no hallucinations springing up, no errors springing up, or if there are errors, I catch them, so it's testable. How do I do that? This is the result I'm showing you. This is more files, right? It's working somewhat differently. The menu now is horizontal. This is kind of nicer. But in principle, it works the same. So the basic functionality is the same. Of course, it's the same requirements. But I did it differently. And at first, I set the stage. I told it exactly what I think the basic building blocks should be. Right? And I didn't ask it to generate code right away, but do you understand well what I'm getting at? This is what I want you to fill out as a template later on. And then I prompted very specific small scopes, like only here. So this is about displaying the histogram. I gave it an example of the histogram. There is, well, this is a schema for this example here. Only that. I need a handler For that, also there's some context above, where the histogram is generated by the processor. So the processor is already a class I'm referring to, and then passed to the UI projection method. So I'm specifically telling it, okay, so here's something within a data flow, and this has to fit right in here. So design is in my head. How I came up with that, whether with support from the AI or just by myself, that's not important. But for getting the code, I need to tell it, okay, this is the context, and I need you to put something right in between. And this is a small object, logic, very focused logic, which is not dependent on anything else. And the same happens here, a function for the UI collection, something to display, and calculating a probability distribution, which is part of the domain. So I'm on top of all the working parts. I'm like a real manager because I'm integrating all the parts, and I'm telling it, don't do anything yourself, but put it, the working logic, put it down into operations. And then we integrate from the bottom up. Plus, of course, I instructed it to generate some tests. That's the result. That's the files. Here, interestingly, I have to understand what clean code means. I have to understand what architecture means, and there's domain logic and domain data. And so there's a couple of aggregates here. I pulled out domain data. See, I have the red clouds down here only. Why there's a red cloud here, I'm telling you in a minute. It's not very important, but I wanted to be honest. This is the classes inside the files. And so there's two classes with red. Here's no class with red. There's data types, no logic. Well, down here, that's okay. If red is in the bottom, that's great, right? No, we pushed it all down. The logic is pushed down to the leaves of the function tree. And this is for, what is this, handle forecast or calculate forecast? Handle forecast, right? So for one function, for one use case, it's the functions which get called, and you see red, 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 red. It's all at the bottom. And here, these shapes, they signify tests. Test, 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 test. There's tests. I didn't put tests here. One test for integration was enough for me here. There's one integrational test here. I didn't put an integrational test here for the plural. I was content with a singular test. With a singular test down here. So you see some kind of red, like a pink cloud here and a pink cloud here. What does it mean? It is dirt. It's a bit dirty. There's some logic up here. It's not pure integration, but there's a very, very simple loop. And it's so simple, we don't care. Really. Don't tell anybody, we don't care. So the real workhorses are really at the bottom. That's what I want to show you. This is radical object orientation. Two principles, principle of mutual oblivion and integration operation segregation principle in action. And this, to prompt for this, creates testable code, understandable code, because each of those functions is very small, it's easy to test, easy to prompt for, easy to integrate into higher levels. And that's where I see that AI can really help us to ease our lives, to not code logic anymore, which is boring. Once you know the overall shape of your software, logic is really, give it to the junior. No, give it to the AI. It's much better. So there are tests here. Yes. And it's all pushed down to the bottom. This is so relieving, really. So, yes, question. The blue is test. That's a test. You see here, there's an integration test because this one is depending on those. But they are so simple. I put the test here. And I put one here because all of this seemed big enough to warrant its own test. But there's no surrogates, no mocks, no fakes. And that's what I'm going to talk about tomorrow when I'm talking about architecture, how this is an evolution of architectural patterns to, in the end, arrive at this. That's next level after clean hexagonal architectures. And what you see in this decomposition tree here at the bottom is actually forming a flow. This is integrated on different levels. See the strokes here. This is composed at different levels, but in the end, in a sense, this is where actually the work gets done. Okay. This is the little dirt in the run simulations. A little dirty logic here for calling this simulation the real workhorse several times, but it's so easy, we don't care. This is a pure integration, that's what we like. Easy to understand, run the simulations, group the simulation results, and then convert them to a probability distribution. That's easy, not intermixed, no functional dependencies. And so going back to the beginning, we have testability, no functional dependencies of logic. We have modularity, small, focused classes and functions, simple dependencies, and organic abstractions, especially the compositions, where functionality gets composed and integrated into higher and higher levels of behavior. In all, this is clean code. If you read this kind of code, it's easy for you to read, of course. And we are forced to use small scopes. And because this all so nicely works together, thanks to L and K, I would say radical object orientation makes for a great marriage between AI and humans. Thank you. Right on time, almost.